morning, everybody. Thank you all for coming to our little Req mini conference within the wider ElixirConf. All right, so my name is Christian. I work for carres.com. Carres.com is a website on the internet. And it may shock you to learn that when you visit carres.com, more than one server is involved in collecting all the data that you need to return the website back to you. I too was shocked to learn this. And you may want to sit down for this next revelation, but gathering all of this data from the wild internet does not always go well. Sometimes servers go down, requests get dropped, or just take too long. And sometimes, a lot of the time, the code we write really isn't up to the task of handling this much uncertainty. So what are we to do in the face of such uncertainty? We drive performance with Req and Finch, of course. But really, we're not going to talk too much about either library today. We won't spend that much time on Req because Wojtek is here. And hopefully you were all in this very room an hour ago to hear him give you a much better explanation of Req than I could give. Suffice it to say, Req is excellent, and you won't be sorry for using it. And Finch we'll speak about a little bit later. So then, you may astutely be asking, what are we going to talk about today? And should I bail for that AI talk before it's too late? So nominally, we are going to talk about HTTP requests and how we make them at carres.com. But really, what we're here to talk about is digging. Pits of success. So why are we digging pits? We're trying to build up an implementation of HTTP request code that is correct by default, and correct being defined by our use cases, which is to say defined by our system. And engineers being who they are, sometimes it's harder than you think to ensure that your code behaves correctly in the face of chaos and both intentional and unintentional abuse. So we're going to dig a hole and hopefully fall into it, a pit of success. Hello, everyone. My name is Christian. And today we're going to talk about HTTP, Req, Finch, and pits of success. I was fortunate to speak at ElixirConf last year. And I guess it didn't go that poorly since they invited me back this year. The selfie was slightly harder to take, but I am happy to say that I'm glad to report that the incidents last year with the birds and the mechanical bull weren't deal breakers. So that's great. There are three themes to today's talk, the things that I hope you leave with. The system is the design, defaults matter, and telemetry is immensely valuable, more valuable than you probably think until you start using it. But first, a promise. There'll be no LLM reveals in this talk. I'm not going to say that Bard or ChatGPT wrote some or all of the slides. So let's talk about the pits of not success that we built and in which we trapped ourselves before we got a working pit of success. So as an aside, for the longest time, I thought the HTTPoison logo was a guy with his arms up to the side, and I only just recently realized it's an actual bottle, which makes much more sense when you think about it. OK. So when you reach for an HTTP library in Elixir, there's a high likelihood you'll get HTTPoison, if only because so much of the prior art already uses it. HTTPoison is a relatively thin wrapper to Hackney, and from here on, I'll use the two names interchangeably. So when I talk about Hackney, consider I'm also referring to HTTPoison, and Hackney is much easier to say out loud. So Hackney works great most of the time. At Carres, we implemented a lot of HTTP modules using Hackney, and many, if not all, of our issues came from our own ignorance and lack of understanding about our own use cases and how to use the library. So one default that really matters is that most HTTP libraries have very generous timeouts. When you don't explicitly set the timeout you want, you can end up with a 10 to 30-second wait, if not longer. And that is probably not great for users. Pooling. Pooling is a challenge to get right, full stop. It's just hard to do. And using Hackney, pools are explicit. On its face, this seems good. But if you don't define a pool for a heavy workflow, one set of requests can quickly saturate the default pool, and this can degrade multiple services and makes for a large blast radius. Hackney telemetry must be opted into with a somewhat involved behavior implementation, and unfortunately, it's not that well documented. Telemetry, as I will reiterate through this talk, is incredibly valuable, and it really shouldn't require much more engineer interaction than a very simple annotation or like a one-line declaration. So these three factors lead us as an organization to repeatedly make the same implementation mistakes over and over. Every new HTTP module has similar and painful teething pains. Our engineering org isn't that big, but it's just big enough that mistakes in one team are likely unknown to another team. And again, it's big enough that we build a new client every 2 to 3 months, and that's just enough time that it dulls the pain from last time, so mistakes get repeated, and it's harder to learn lessons. With our current implementations, we don't have any kind of flow control. So think regulator, or think a circuit breaker. Some way to fail fast if something has happened and we think the downstream service isn't working right. So this broadly outlines the shape of our system and gives us some guardrails for the hopefully improved implementation that we're going to create. And these are the challenges that we have. And we think we need to switch to a different HTTP library, but to the first question, the answer is both yes and no. As you'll see, as we'll discuss, we don't need to do all that much that's very different. We could make it work with Hackney, but using a different library is also an important signal. It signals a difference, so our engineers will know that this is maybe not going to behave the same as that. Two things aren't going to be equivalent. It helps point the way to the pit of success. So let's go exploring. There's a surprisingly large number of HTTP libraries in Elixir now. And honestly, given the menu, there's not a great way to give a fair evaluation to each of these clients. So we'll just have to pick one that seems promising and be willing to be wrong. After some light surveying, we target Finch as promising. Finch uses a supervised process, but it's entirely functional and doesn't rely on cross-process messages as in a gen server. Finch is built on top of Mint and Nimblepool, and again, sort of as that bullet point, they don't try to copy messages across processes if possible. So let's see what we can do with Finch. As another logo aside, that's a beautiful logo. So the first pit we built for ourselves was an attempt to use GenStage to manage our HTTP clients. So GenStage is great. It's a really powerful tool. And it'll definitely work for managing HTTP clients, but maybe this isn't going to be the right way. Let's see. Let's talk about it. Before we talk about GenStage, let's talk about some hard problems. We're using GenStage and HTTP. So of course we called it HTTP on GenStage, or hogs. The quickest description of GenStage that I can provide. GenStage has a producer, which doesn't strictly produce. It fetches work to do and gives it as a batch or to a consumer, only upon request. The consumer requests the work from the producer and executes some work, possibly in batches, and then requests more work. So returning to our system, let's describe the type of HTTP calls we need to protect here. Namely, calls that satisfy a user request somewhere on cars.com. This means that the inbound work queue is potentially unbounded. GenStage by design creates a single process bottleneck. The consumer requesting work creates back pressure and slows down the flow of work to ensure it's not overwhelming for the GenStage consumers. This is great when you're using it to manage some amount of async work, but that's not the workflow we're trying to use this tool for. And for the inbound queue, GenStage can sort of manage a queue at the producer level, which it calls a buffer, but that's not really what it's intended for. And the producer should be the thing that produces work on demand. And if it's just sitting there, holding on to some HTTP request until a consumer happens to be available, then really all we've managed to do is introduce latency. It also precludes parallelization, as the producer must remain a single process. GenStage is also not intended to be synchronous. So when you ask the producer to do work, that's a cast by design. It's a fire and forget asynchronous task. In order to have the consumer stage go out and actually make the HTTP request and pass it back to us, we need to return a ref to the calling process, and then the calling process needs to sit there and patiently await the response from the consumer. Users don't mind waiting, right? I mean, we don't want to overwhelm them with a web page that's too fast. Finally, HTTP messages or HTTP requests as process messages can be big messages. They're fat. We need to send the messages across process boundaries where they'll get copied from one process to the other and remain in memory until they get garbage collected. Recall Finch explicitly tries to avoid cross-process message copying as a top-line feature. So most of these are problems that you can mitigate one way or another, but we're working against GenStage the whole way. The system is the design that's going to inform us about what we're doing. We know how we need to make web requests. We need to find a framework for the system rather than trying to hammer our use cases into a framework they weren't built for. Fighting your framework is a really efficient path to weird edge cases, bugs, and other undesirable behavior. It's a bad code smell, but it can be a subtle one, and you have to keep a close eye out for how much you're trying to do something that your framework wasn't made for. And like many things, this happens by degree. One extra clause here, some light monkey patching there, a non-standard usage over here, and before you know it, you've hacked yourself into a corner and turned a sleek tool into a Franken tool with a bunch of heads bolted on. Let's talk about Tesla. Not that one. Tesla is an HTTP management framework that's inspired by the Ruby gem Faraday. They both use the idea of pluggable middleware to add functionality to a request stack. This seems promising. We get to a working Tesla implementation in pretty short order. The plug and middleware approach is actually where we run into an issue, namely this. Macros make the configuration of the HTTP stack a compile time concern. And normally this would be fine. But we make liberal use of the application runtime environment to set values for API keys, host names, etc. So when we have an application variable, because it's being passed to a macro, we have to use compile-env to set the value. So in staging, we might set the key like this based on some system environment variable. And then in production, we would override it with a different variable. So this is also a real production secret, by the way, so everybody be cool. Compile time values don't update the compiled value based on a change to the environment. There is tooling in place that helps this, but fun fact, if you use distillery, it doesn't help you, because this is the feature and not the bug, that you can just change the environment variable and it's not going to complain about those underlying changes. So getting the values wrong for the deployment is a real possibility in this situation. And trust me when I tell you, you'd prefer not to call your staging environment when you're in production or vice versa. So the compile time evaluation of values adds a fair bit of complexity to our HTTP implementation. It's not insurmountable, but it adds to the overhead of things you need to know and implement correctly to ensure that they behave the way you want. In order to help keep the evaluation of application variables a runtime concern, we end up wrapping the macros in callback functions. And if this sounds like too much metaprogramming to you, then you are 100% correct. It also requires a fair amount of understanding from the users. While callbacks are a reasonable way to make an API contract explicit, they also shift the configuration into an upfront concern. We're hoping to have a cleaner semantic for this API. Callbacks put too much onus on the engineer getting it right every time they make a new module, and callbacks invite undesirable copy-paste errors. This also implies that our use cases are not completely in sync with the design of our library. Again, it's not a deal breaker, but it's a concern. Finally, Tesla has, at the time we used it 15 months ago, a challenging testing regime. It sets a Tesla mock into the process dictionary, and this is the global mock. This makes async tests particularly challenging, either impossible or inconsistent and flaky, and it creates some and for other reasons, it creates difficulty when testing timeouts. Timeouts being one of the settings that we very much care about and want to be small. We did make Tesla work. We even committed it to main, but we won't succumb to the sunk cost fallacy, so we'll rip this right out of our code. Let's keep looking. Req has a very similar design to Tesla, but it uses functions to mutate the HTTP request. And hopefully, everyone was here an hour ago to learn all about Req. Req is a batteries-included HTTP client for Elixir. It's a nicely opinionated framework, and it seems like the design of the library is better aligned with our use cases. Because the Req components, called steps, are just functions that you can add or omit, the question of compile time dependencies is mostly obviated. Req also uses Finch by default. So we asked ourselves, what if we take an opinionated HTTP framework and make it even more opinionated? What settings and Req steps would we need to add or remove or configure? Recall, the system is the design. So what does our system tell us about the framework that we need? So short timeouts, no retries, pooling, telemetry, and some kind of a circuit breaker. Let's talk last things first. So circuit breaker. A circuit breaker is a form of load shedding. Based on some criteria, we open the circuit, and the request will fail fast instead of taking the full amount of request time to fail slower. We opted to use Fuse. Fuse is a tight little Erlang library that runs one process per fuse to maintain the state. When bad things happen, you send a melt message to the fuse process, and if enough melts happen within a specified window, the fuse is blown, and subsequent calls through the code path fail fast. Failing fast offers two benefits. So you reduce the pressure on the downstream service, helping to alleviate the thundering herd, and you reduce the amount of work done locally, reducing resource blocking, when you're in a state where the result from the downstream service is less likely to provide good data. We wrapped Fuse in a plugin for Req, which you can use yourselves. It's available cars.com/recfuse. Retries. Retries are undesirable by default. Any HTTP module could retry, but it's up to the specific module to opt in. Timeouts, as I said, most HTTP libraries, including Req, Finch, and Mint, have very generous default timeouts, and this is not what we want. And there are several timeouts to be aware of. There's the connection timeout, think TLS or SSL handshakes. Periodically, this takes much longer than a connected request, so it's important to consider how long you want to wait for that initial connection. In our experience, this connection timeout had a disproportionate impact on the slow tail of the distribution. Pool timeouts is the time it takes to check out a connection from the pool. On average, you would expect this to be trivial, but if things are going poorly, you have a saturated pool or a system under extreme load, then this is an important timeout to have in place. And then there's the receive timeout, which is what I think of. This is the time it takes to receive a response from the downstream service. This is what I think of when I think about HTTP timeouts. Additionally, the various timeouts are added together. So in the worst case, your user could wait 30 seconds plus 5 seconds plus 15 seconds for the whole request to return, probably with a failure at that point. And telemetry. Telemetry is simple but valuable, emitting timestamp markers at the beginning and the end of some function call. Finch emits its own telemetry, and the combination provides really helpful insight into the running state of HTTP code. I didn't appreciate how valuable this could be until we had a bunch of services emitting telemetry. So we take the telemetry generated by our clients and make a service page for every implementation. Now that we have most of the pieces and settings we need to ensure our requests remain well behaved, how can we glue them all together? Friends, I give you Req by cars.com or carre. So based on all of our use cases, the system, we were able to define the traits that carre needs, the defaults to work correctly, and help us to dig the pit of success for the next use. The most basic feature is probably the most important. Carre sets default values for everything that could impact the request. And if that's all carre did, it would be a pretty big improvement. A circuit breaker was a new but important feature on that list. And having a circuit breaker as a no configuration needed default was a key requirement. We want to support optional user overrides, but we can't expect every or really any user to read our docs, to read the Req docs, to read the Fuse docs, and understand the somewhat complicated configuration of a circuit breaker. And telemetry. Telemetry, as I will repeat, is incredibly valuable. So with carre, we built with a very simple semantic in mind. If you needed a basic HTTP client, the minimum of code you need to write is use carre, and you'll have a nicely configured module. This is the end result, and while we were aiming for something like this, of course we didn't know that when we started. Once we had the ideas that comprised the design, we had to implement it. So this really just describes like lowercase a agile engineering, and I'm not going to belabor any of this, except for one point that I will emphasize is eating your own dog food. Once you build the tool, you have to use it, and you have to use it a lot, not just to prove that it works, but to drive out bugs and improve the tool itself. We re-implemented many HTTP libraries to use carre. Each of these clients emit their own telemetry, thus adding more diagnostic information to the instrumentation system. In addition to many in-application uses, I'm happy to say we updated our Elasticsearch fork to use carre as the HTTP library, and we also use carre to send our telemetry to Datadog, which of course emits its own telemetry. We use the instrumentation generated as a dashboard and build one up automatically for every module that uses carre. And we didn't have anything like this at a specific module level. So this dashboard helps to make performance easier to monitor and empower individual teams to monitor and tune their own code. The client options is the one callback that remains in carre. It provides a means for the client to set any values that might need to be based on application configuration. And it helps mitigate configuration, the risk of configuration that may or may not update based on changes to system environment. So it took building hogs and throwing it away, and working with Tesla and throwing it away, to get to a point where we had a really well-defined idea of what our framework needed to do, and to discover inside of what boundaries we were working. We had to understand our own system better in order to better describe the shape of the project we were building. One of my favorite things is to delete code, especially my own. You have to be willing to kill your darlings in order to discover the version of whatever it is that you're working on that's the best, or at least good enough for the problem at hand. Writing code that we didn't keep helped us to more completely understand our system and inform the design of carre. The system is the design. We actively avoided fighting against HTTP libraries and our own system. We were trying to improve an aspect of our application and not execute a stealth rewrite of some significant percentage of the code base. Nor were we trying to write the one true framework and then force our way on everyone. For every setting that we're aware of, and which is settable in Req, Finch, and/or Mint, we picked a sensible default and ensured that it was set. As much as we think carre is right for every use case, of course it won't be. So everything can be overwritten from the implementation. And emitting telemetry on top of the system discovery provided more information about the possible ranges of settings that would make sense for our use cases. Think timeouts. The telemetry allowed us to better calculate the arrival rate and service time of our system itself. Hey, that sounds like Little's Law. A little aside. Little's Law comes from queuing theory and describes work or customers or requests flowing through a system. To quote, in most queuing systems, service time, W, is the bottleneck that creates the queue. If you think in terms of a website and you rearrange the terms, you can use it to provide an estimate of the traffic limits of that site. Little's Law is simple, but it's powerful, and once you learn about it, you see it everywhere. You see so many problems that are described by Little's Law. Okay, we're nearly at the end of our talk, so if anybody would like to get in touch with me, I can be reached. Okay, no. Yeah, don't go there. Was social media a mistake, everybody? I'm sort of starting to think it was. You know what? I'm on Elixir Slack, and I would be delighted to talk with anybody. The QR code is a link to my Elixir Slack profile. So while Req and Finch are great libraries on their own, they're not magic. They won't prevent you from making bad choices or stumbling into painful uses. With carre, we were focused on driving performance for our system within the real world, by which I mean it's actually pretty difficult to improve HTTP requests. Most everything happens outside of your system. At best, we're optimizing around the edges, but that's the space in which we can have an impact. To reiterate a point from earlier, if all carre did was set short timeouts, then it could have a big impact on the slow end of the distribution. And improving the times for the P95 plus, sort of the slow end, has a real impact on user experience. Recall, a distribution like this isn't describing 95% of users, it's describing 95% of requests, some of which, statistically, are mine. And I'm impatient. To help address my impatience, we had to change some things. We had to be able to measure so we can know if we're helping. And in changing things, we're willing to be wrong. For me, there's nothing more instructive than writing code that doesn't work or that you throw away. So by setting defaults, emitting telemetry, and working within our system, we drove performance and crashed our carre into a pit of success. Thank you.